Okay, right. See, actually, you have to understand that basics technique. What is that base technique and why it is coming into picture here? So basically, we know this. If this is the starting point, this is the starting point. F of w given t, which can be written as f of t given w into f of w whole divided by what? F of t. This is what the right. So in this, we know this is already, and we already modeled this as a Gaussian. We know what is that mean and variance individually for T1, T2, T3, and so on. I put this T. But the mean is, they're all Gaussian. In general, for example, if I consider this, so that is going to be the Gaussian with mean as y of xi, and the variance is 1 by beta. It is like that. For f, right, and they are independent. The observations T1, T2, T3, and so on, they are all independent. In fact, if I find this covariance matrix for this, right? If I form a T vector here with T1, T2, and so on up to this Tn, arrange it in a column form. Remember that they are all the random variables. And you find this expectation of T minus T, if expectation of T, the whole transpose, right? So n cross matrix, which is of n cross n. If I find out this and treating that T1, T2, T3, they're all the independent event, right? And having identical distribution, right? So they are having means differing y of xi, but the variance is going to be the same, 1 by beta. If that is the case, if I find out this covariance matrix for this T, the diagonal matrix, which is given as I. So what I'm trying to say here is, you get in the diagonal form like this, beta is arranged in the diagonal form, and all other elements are going to be 0, and matrix is of size n cross n. This is the covariance matrix T, the random vector T, right? So this is for your information. If because f of t given w is already, we understood that it is Gaussian. The variance is also there for the individual ti's. If I come together as a random vector, and if I write it as what is that covariance matrix, we get this result. This is a diagonal matrix, right? Now, in case of Bayes technique, what is more important here is, this is already known. Even in likelihood, maximum likelihood function, this is 2, whatever I told. What is more important now is this f of w. So modeled as Gaussian, right? So that is the important point to, in case of this Bayes technique. What is more important is this f of w is also Gaussian distributed. This is also multivariate Gaussian distributed with mean vector m naught and coefficient. This is a variable what we have given, right? With mean vector m naught and then covariance matrix S naught. We are assuming that it is having some covariance matrix and having some mean vector m naught. If that is the case, if I have this f of w going to be what? Gaussian distributed with mean vector m naught and covariance matrix S. then your f of w given t is also Gaussian. That is what I'm telling, right? And that is also going to have mean vector and covariance matrix. Let us say this mean vector is Mn and the covariance matrix is Sn, right? Okay, so this is what I am trying to say now. You have to understand the notation, what I am telling now, right? So the mean vector for this one is represented as what? Mn, and the covariance matrix is represented as S subscript n, right? And you see that f of w is assumed as what? Mean vector m naught and covariance matrix S naught. If that is the case, then m naught, mn, sn, m naught and s naught, they are related like this. Mn can be written as Sn. Sn is what? Sn is the covariance matrix of the positive density function. That is what I'm Gaussian, multivariate Gaussian density function with mean vector m naught and Sn as a covariance matrix. They are related with what? S naught, m naught, right? And you know this variance is also coming into picture. It's coming because you have the term f of t given w, right? So that is having the density function. That is having the density function with mean what? Xi and variance is 1 by beta, and that is the reason this beta is coming into picture here. I'm trying to say here is f of w given t is also Gaussian with mean vector mn, and covariance matrix Sn can be related to, right, the covariance matrix of f of w, which is S naught here, right? So Sn given as beta 5 transpose 5 the whole inverse, right? 5, the whole inverse means this whole thing is getting having that inverse term in it, right? So now I would like to, I think we will discuss this one in detail in the next class. I just wanted to wind up today's class by asking only one question. So you are given Mn and Sn, right? And they have a relationship. If so, what is the estimate for, or base estimate? I'll put it as, what is the base estimate for W? Who is telling? You are given Mn and Sn. They are related. They are related with S naught inverse, right? They are related with m naught. Beta is also coming into picture, and you know what is basis function here. Everything is there, right? So now my question is very simple. You are given Mn and Sn. You computed this. Then what is the base estimate of W? You know, likelihood estimation and all, right? But now I'm asking, what is the base estimate? Base estimate means what? The conditional mean, right, of this f of w given t. Unfortunately, this f of w given t is Gaussian. So conditional mean, conditional median, and conditional mode, all are going to be the same only. All the three are going to be the same, identical, because when it is Gaussian distributed, mean, median, mode, everything will come into the single point. The same value only will come. It is the median, this itself is a mode, this itself is the median and mean, median, mode, right? So if I have a positive density function, the conditional mean and conditional median and conditional mode all are going to be the same. So in that case, what is the estimate of W? Who is telling? If you tell this, then you are in the proper track. Otherwise, I have to discuss everything in the next class. Anyway, discuss this one in the next class. But somebody type in the chat window, what is the estimate of the random vector W? Are you able to hear? Can you guess? Which one is Gaussian, Sanjay? No, no, I am asking, yeah, Mn. Excellent, excellent, excellent. Krishna Sai Tarun, which department you are? Krishna Sai, you are easy, okay, right. So it's excellent. So at least, I am getting the feeling that you are able to understand, right? So next class, anyhow, we are going to discuss this base technique in detail, right? So Krishna Sai Tarun, as he said, right? Mn itself is the estimate. Excellent. Excellent. Mn itself is the estimate. So you are in the proper track. Mn itself is the estimation. So your W cap is Mn itself because it's a mean vector. It is a mean vector, right? Okay. It is a mean vector, right? Wait, which one? Which one? 1 by beta? I don't understand it. Oh, here. You are talking about. Anyhow, this one, anyhow, I'll discuss in the next class. Now, I think it is time, right? So, because I will explain about the covariance matrix and the mean vector in the next class, right? For some arbitrary random variable, and then for independent, and then uncorrelated, independent and uncorrelated. If it is a Gaussian multivariate Gaussian distribution, if it is independent, it is uncorrelated. If it is uncorrelated, it is independent. If it is independent, it becomes what? Uncorrelated. Vice versa is also true only for Gaussian. Vice versa is also true. If it is uncorrelated, it becomes what? Independent. And these zeros, right? The covariance matrix, these off diagonal elements are zero because they are uncorrelated, right? So T1, this is basically how this random variables Tn, right? This is Tn here, and this is T1, T2, and so on up to this Tn. How this T1 and T2 are correlated? That is the question, right? So it is basically expectation of T1, T2, right? Right? So minus expectation of T1 into what? Expectation of T2. So that is actually becoming zero. That is what this matrix is becoming diagonal, right? So, but variance, expectation of T1 square minus expectation of T1 whole square. This is the variance, and we assume that the variance are going to be the same for all the elements T1, T2, T3, and so on up to this Tn, and hence the values are going to be 1 by beta because we assume that the variance is 1 by beta, and we have chosen purposefully 1 by beta just to make beta to come here comfortably in this expression. Otherwise, you will have 1 by beta in this expression, which may not look good. So that is what we have chosen 1 by beta as a variance of, right, the noise, and hence beta is coming in this expression comfortably, right? So as I think I forgot, I just see that Krishna Sai told, right? That is the important thing what you understood. If you want to, if you are actually getting home, right? So what is that you have to understand from this today's class is this part, this one. This is this one, right? This itself is, this is the estimate of W. Because we are actually doing linear regression problem, we are interested in estimate W, right? So estimation of this W, estimation of W is W cap, that is equal to Mn itself. That's all, the problem solved. Mn itself. We'll discuss how this is related with regularization in the next class. I will once again explain all the things, but as of now, you have to understand that the estimation of W is Mn. That is what that final answer, right? So we'll, yeah. I'm not giving any yes, not, and yeah. F as a distribution, f of t given W, f of W are Gaussian. F of t given W is Gaussian, fine. F of W is also Gaussian, right? The covariance matrix S naught is related with F of W. We can't say anything about the diagonal or not, that one. We can't say anything about that, right? F of t given W, that covariance matrix is diagonal. F of t given W, right? So this one having this mean vector is going to be like y of x1, y of x2. This is the mean vector, right? Y of xn, and this is the mean vector, okay? And the covariance matrix is, right? Okay. And then covariance matrix is basically, where is it? Yeah, the covariance matrix is this one, right? So that we are not giving any explicit expression for it. So let me write it as a matrix itself, like it is a 1 by beta in the diagonal, and off diagonal elements are going to be the 0 in this. Okay, so it is like that. So we are telling the information regarding f of t given W, and f of W we are not restricting anything to m naught and s naught, right? We are not restricting anything to m naught and s naught. In the next class we will restrict the yes.